Okay, so let's go ahead and continue with this problem. So one thing we want to note is that once the cheetah catches the gazelle, they have both moved the same amount of distance, okay, over the same amount of time. So what we'll do is we'll first treat them separately and then equate them in order to solve for this, distance here, or sorry, time, okay? How long it takes to catch the gazelle. Okay, so I'm going to say that I can use two different equations. So let's see. My acceleration of the gazelle is 0, right? Because it's moving at a constant speed at 10 meters per second. So this is our velocity here. Okay? Of our gazelle. Put a little g there. And so for our gazelle, I'm just going to put a g, we can say that our x equals x naught plus vt. This is the equation we can use in order to solve for our time. Now for the cheetah, on the other hand, we have to take into account their acceleration. So we have x equals x naught plus v naught t plus 1/2 at squared. Okay, we have to take account into the acceleration, okay, because we don't know how fast the cheetah accelerates to. Okay, so these are our two equations that we're going to use, and remember that when the cheetah catches up to the gazelle, our delta x of the gazelle is going to be the same as delta x of the cheetah. Okay, assuming that where the cheetah was lying is the 0 position. Okay, the initial positions. Okay, so solving for delta x over here, it is going to be vt, and delta x here is going to be equal to, well, our v naught is 0, so it's going to just be equal to 1/2 at squared. And then we can equate these two. Okay, so these two should be equal, so we get v times t equals 1/2 at squared. And then we just solve for t, and we find 2 times velocity divided by acceleration is our time. Okay? This is all for part A. So then we can plug in our values. So our velocity is going to be 10 meters per second divided by our acceleration, which is 4 meters per second squared. So we get that our time that passes is 5 seconds. Okay? Sorry, that was a little sloppy. Now for part B, it asks what is that displacement of the gazelle and the cheetah. So, because they are the same, we can use either of these equations to solve for that displacement. I'm just going to use this one because it looks a little easier, but they should be the same. So delta x is going to equal our velocity, which was 10 meters per second, times our time, which we just solved for as 5 seconds. So our change in position, or our displacement, is 50 meters. Okay? So this is an example of the two-body pursuit problem. Okay, so here comes one of the main ideas of the course, and that's going to be free fall. Okay? This is going to be the idea that if air resistance and friction are negligible, okay, small enough to ignore, then in a given location, all objects fall toward the center of Earth with the same constant acceleration, independent of their masses. Okay? this is the idea of free fall. It's going to be an object falling without air resistance or friction. Okay? So again, any object without resistance or friction, okay, we have the same constant acceleration, not depending on their masses, okay? And the acceleration due to gravity on Earth is going to be equal to 9.81 meters per second squared. Okay, so this is the acceleration of free-falling objects, and this is going to be constant. Okay, we're going to treat it as a constant. Kinematic equations for objects in free fall, where the acceleration is negative g, where the positive direction is upward. They are listed here. Okay. Notice the similarity to the other equations that we were working with, okay, the equations of motion. We just plug in negative g as our accelerations. Okay, so this is assuming that we make this positive y, okay, so that our acceleration is this, negative g, okay. Now when we're just asking for g, that is just going to be this constant here, okay. All right. So this is going to be our problem-solving strategy. So first we want to decide on an orientation of the coordinate system. Okay, so what sign is going to be the acceleration of gravity? Is it going to be positive or negative? We like to put it negative so we can be consistent with these equations. Okay, so I would say, like if this was my problem, I'd say, okay, this is going to be positive y. Okay, we want to draw a sketch of the problem. So if we have a ball falling, we can go ahead and sketch it. That helps us understand what is going on. Okay, then we want to record the knowns and the unknowns from the problem description. You may have noticed me doing that already in other problems. It really helps to plot out what we're looking for, what we know, and so forth. Okay, then you want to decide on what equations you need to use in order to solve for those unknowns. So if I have my x position, initial and final, and I have my initial velocity and final velocity, but I don't have time, okay, we can go through and decide which equation we can use to solve for that time. Okay, so you just being able to plot out your knowns and your unknowns really helps you determine which equations you need to use to solve for those unknowns. Okay? All right, so let's look at an example here. This is a tennis ball in free fall. Okay, so as the tennis ball travels through air, what does its speed do? Okay, so if we have this tennis ball, it was thrown up and then it falls back down. Okay, what does this speed do? Does it stay the same? Does it increase? Does it decrease? What is it doing? Okay, hopefully that gave you a little bit of time to think about it. Okay, so as the ball travels up to this maximum position here, our velocity is actually slowing down this entire time. Then as it comes back down to Earth, it speeds up. So it decreases, then it increases. Okay. Now, instead of doing some more of these theoretical examples, I'm going to go ahead and give you an example from the book. So this is example 3.14. The figure shows the positions of a ball at 1 second intervals with an initial velocity of 4.9 meters per second downward that is thrown from the top of a 98-meter high building. Okay, how much time elapses before the ball reaches the ground? what is the velocity when it arrives at the ground? So we're going to use those equations that we saw in a couple slides back in order to figure this out. Okay, so we have our time when it reaches the ground is 4 seconds. The final position, x, is negative 98.0. Okay. And this actually already tells us the velocity when it reaches the ground, but we're going to ignore that. Okay, so we know that the initial velocity is 4.9 meters per second. We know g is just 9.8 meters per second squared. Okay. So let's see. We know x, v naught, and t. And we want to, actually, we don't know t. That's what we're looking for. It states it here, but we want to solve for that, right? Okay. Sorry about that. Okay, so we're going to go ahead and use one of these equations. We know our initial velocity and our delta y, right? Yeah, delta y is going to be that. So y equals y naught, this is part A, y equals y naught plus v naught t minus 1/2 gt squared, and let me double check that. Yes. Okay. So our initial velocity is 4.9 meters per second, and it is downward, so it's going to be negative here. Okay. Our final, final position, could put a y instead of the x. That's going to be 0. So we have negative 98 meters equals 0 plus v naught, which is negative 4.9 meters per second, times t minus 1/2 9.81 meters per second squared times t squared. Okay, so we have a lot of values here, or a lot to this equation, and we want to solve for t. Okay, so what we'll need to use is the quadratic formula in order to do so. Okay, so I'm going to go ahead and rearrange this a bit, and for now I'm going to ignore the units here. Okay, so I'm going to say negative 1/2 times 9.81. I'm going to go ahead and round that to 4.9 t squared minus 4.9 t plus 98. Okay, so now we're going to use the quadratic formula in order to solve this. So t equals negative the b, which is negative 4.9, plus or minus the square root of b squared, which is going to be 4.9 squared, minus 4 times a, which is 4.9, times 98, divided by 2 times negative 4.9. Okay, so you can go ahead and do this in your calculator. Let me do that real quick. All right, so I went ahead and quickly did that in my calculator, and I got 4.9 plus or minus 44.1 over 9.8. Now, the plus or minus, you want to just remind yourself that time can't be negative, so that'll definitely tell you which one to use. And in doing so, I got that time is equal to 5 seconds.